Hi guys, in this unit we're going to look at magnets and magnetic fields. Magnets and charge have a lot in common. In fact, it's moving charge that causes a magnetic field to exist. And just like we know two charges can interact at a distance, if we had a positive charge here and we brought another positive charge here, we know that there will be a repulsive force between those, and we say that's because we have this electric field that's emanating from this one, and this field exerts a force on that charge and pushes it away. If there was a negative charge here, the field would exert a force on it and pull it in, right? So it's the field of one charge that interacts with the other charge and allows a force to act. The same thing happens with magnets. There is a field around a magnet, and it interacts with the other magnet. And so we think of a magnetic field as emanating from the North Pole. And so there's a magnetic field coming out of this, and it repels this magnetic North Pole. However, it would attract the South Pole. So we know two North Poles will repel just like two positive charges will repel. We know two South Poles will repel just like two negative charges will repel. But a North and a South attract just like a positive and a negative attract. Probably nothing new here. Also, there's a really big difference between charge and magnets in that we can have a positive charge and we can have a negative charge. We don't get just the south pole of a magnet. If we take a magnet and we cut it in half, we end up with two smaller magnets. And you can keep cutting that in half and you keep getting two smaller magnets. There has never been a magnetic monopole, so just a north pole or just a south pole ever observed. So you always end up with a north pole and a south pole, never just a north pole or just a south pole. Now, magnetic field lines are helpful, and we're going to use them quite a bit when we're trying to figure out things that are related to charge and current. If we were in school and you got to do this lab, you would actually see that when you put iron filings around a bar magnet, they take on this shape. And if you were to put a compass around there, you can see the compass needle also follows the shape of that line. And so these are magnetic field lines, which we think of as closed loops. The loops continue through the magnet. They emanate from the North Pole, go around, and come back into the South Pole. And then they continue through this magnet. And it is true that the more dense the lines are, the stronger the magnetic field. And so if we put something that's iron out here, it's going to be attracted in this. It's going to have a force exerted on it in the, tangent to the field. So if I put another north pole of a magnet right here, the force is this way because tangent to these fields is that way. The north pole of a magnet, so this is a compass, right? And so a compass works because it's just a little bar magnet that is suspended on its center of mass so it can easily pivot. And it points north because it's attracted to Earth's magnetic field. But if you think about that, if the north pole of a magnet points towards the north pole of Earth, it's attracted to the north pole of Earth, that must mean the magnetic south pole is actually near the geographic north pole. So Earth's magnetic field is much like a bar magnet. We think it's created by flowing charge in the core, and it creates or generates this magnetic pole up here that we use to navigate, right? Our compasses point that way, but magnetic north is actually down here. You can draw magnetic field lines for various different bar magnet arrangements. If we take a north pole here and we put a south pole here, then we get this, right? So they emanate from the north and point towards the south. If we were to take two north poles though, so I have a north here and a north here, what's going to happen? Well, just like electric field lines we think of as not crossing, we're going to think of these magnetic field lines as not crossing. So they're going to push against each other, and we're going to get something like that. And so you can kind of visualize these now. These are going to flow around, right, and back into south because they are loops. We're just going to distort this field. So instead of it going all the way this way and back out and around, it's going to get pointed up. Okay, so the magnetic field lines are going to interfere with each other. Now, the most probably interesting thing about a magnet is that yes, there are permanent magnets. Iron makes good permanent magnets, but it's the magnetic field that's caused by current that we're going to be really interested in. And so just a static charge doesn't produce any kind of electric field or sorry, magnetic field around it. But if that charge starts to move, if it's a current, if it's a flowing charge, then it does generate a magnetic field. And what these pictures are trying to illustrate is the shape of that magnetic field around a current carrying wire. But that's easily done here with the first right-hand rule. And so there's going to be several right-hand rules that we learn, and these right-hand rules are going to teach us about the directions of forces or the directions of field lines in various scenarios. And this right-hand rule tells us the direction of a magnetic field around a long straight current carrying wire. And it says basically point your thumb in the direction of conventional current. Now remember, conventional current is the flow of positive charge. So even though the electrons are moving the other way, we think of positive charges flowing this way. And then your fingers curl in the direction of the magnetic field. So along a current carrying wire, the magnetic field is actually circular. There's concentric circles here, right? The further out we get, the weaker that field is. But these magnetic field lines do actually have a direction, and so they are circular around that. Now I want to draw a little picture over here. If there is current carrying in this wire and in the arrow's direction, then there are also magnetic field lines, and some of them are in front of that wire and some of them are behind that wire, and some of them are into and some of them are out of the page. Now if you think about this, if you take your right hand and you point your thumb in the direction of that wire and then you curl your fingers, the way your curled fingers go tell us the direction of the magnetic field, which means over here on this side the magnetic field is coming out of the page. And so the way you draw a vector that comes out of a page is you make it look like an arrowhead, right? So you have a circle with a point at the top of it. So that shows a magnetic field line, or actually any vector that I want, coming straight out of the page towards us. But then it wraps around and goes into the page on this side. And so this side has to be the arrows, feathers, so the fletchings. And so you get these X's. And these X's represent field lines going into the page, or vectors going into the page. And so what we actually have are some magnetic field lines that come out of the page, go into the page, and then they would wrap around, right? So they're going like this. But if we're just looking at the plane of the page, then they're coming out of the page over here, and they're going into the page over there. Okay? So right-hand rule, if the current's around this circle, we put our thumb in the direction of that, our fingers curl, so as magnetic field lines are going to be coming out of the circle that way. Now, this is an interesting thing. An electric charge, a moving electric charge, generates an electric field and a magnetic field. And because of that, Newton's third law says, well, if moving charge creates a magnetic field ought to put a force back on moving charge. And it's true, that happens. So this is a horseshoe magnet, and it shows us our north pole, and then we bend it around the south pole. So there's magnetic field lines coming this way. And what happens if we put current through this wire is this wire actually gets pulled down across that field. And this way, the current, if we reverse the current, then we get a force up. And so there is a force on a current carrying wire when it's perpendicular to a magnetic field. And the force is perpendicular to both current and magnetic field. Okay? Now, a magnetic field gets the symbol B. It's a vector, and we'll look more at that in just a minute. So that's what this is. That's magnetic field. And so this second right-hand rule 2, is actually about the direction of a force. So the way this one works is you point your fingers in the direction of current. And it's right-hand rule, so you're using your right hand. So fingers in direction of current. And then you curl your fingers in the direction of the magnetic field. And then your thumb will give you the direction of the force on the wire. So over here, the current is into the page. So if you take your right hand and you orient it so that your fingers are pointing towards the screen, and then the magnetic field is to the right, then you would have to hold your thumb down so your fingers can curl right, and that tells you the force is down. And then over here on this one, the force is up, so if the current's actually out of the screen towards you, you point your fingers that way, and then again your fingers have to curl right, and in order to do that your thumb has to point up. So fingers in direction of current, and then curl in direction of magnetic field. And so this is actually going to allow us to sort of state a relationship between magnetic field, current, and force, and it's going to allow us to define magnetic field strength. So the force on the wire depends on the current, the length of the wire in the field, the strength of the magnetic field, and its orientation. Now, if I have a magnetic field that's going this way, and I put a wire in there that's carrying current, and that wire is also this way, there's actually going to be no force on that wire. It turns out that the sign of the angle between them is fairly important. And if the angle between the magnetic field line and the current is 0, sine of 0 is 0. So the maximum force we get is when the current is perpendicular, right? So we're actually measuring this angle here, or this angle here, between magnetic field lines and current. Now, the strength of the force is related to the current in the wire, the length of the wire that's passing through the magnetic field strength, and that angle. And so most of the time we're going to probably deal with perpendicular things. It gives us our maximum force. But this equation defines the magnetic field B. B is measured in Teslas. And I should lowercase that since we're talking about the unit, not the person. But then when you abbreviate it just like newtons, it's capital. So a Tesla is a magnetic field strength. There's a couple old units for that. There's a Weber, which is, Weber per meter squared. So a Weber per meter squared equals 1 Tesla. And there's a Gauss, which is just a different system, CGS. It takes 10,000 Gauss to make 1 Tesla. But magnetic field strength is measured in Teslas, and it turns out 1 Tesla is equal to 1 Newton per meter amp, or amp meter, I guess. And you can do that if you just solve for force here, or B in this equation, right? So B is equal to force over IL sine theta, but that's just a number. So I've got newtons per amp meter.